All right. Good morning, everybody. Welcome at this webinar on field failure data collection methods. The webinar was created by Bill Goebel and myself. My name is Iwan van Beurden, and we are both in the Exeter Sellersville office in the state of Pennsylvania in the United States. So for us, it's good morning, but I saw some people out of Europe dialing in. So good afternoon, and one of my colleagues out of the Singapore office, I saw him online as well. So that's a good evening, almost a good night. The webinar, as I said, was created by Bill Goebel and myself. For those of you who are not familiar with Bill Goebel, he has over 40 years of professional experience. And as he always liked to say, only half of that is in functional safety. So that's quite some experience for a person in functional safety in a field that is still relatively young. Myself, I'm Iwan van Beurden. I am the Director of Engineering at Exeter, and I'm responsible for the development, maintenance, and certification of our Excellencia Safety Lifecycle tool, as well as our SILSTAT software, our live event data gathering software. I am responsible for that portion. I'm a member of the ISA S84 committee, and I perform a variety of 61508 and 61511 related tasks, ranging from assessments, certification work for product evaluations, as well as SIL selection and SIL verifications. And I'm an instructor both for Exeter as well as for ISA. I assume that most of you are familiar with Exeter. We are a global company with several offices around the world. We have some main offices in the North Americas, in Canada, United States, and Mexico, as well as in Asia Pacific region, specifically in Singapore, and in Europe, in Germany, and in Switzerland. We have our main offices. Then we have some regional offices, for example, in the Houston area in the US, but also in the UK, in the Netherlands, and in Rio, in Brazil, in Japan, and in New Zealand. So we have a worldwide structure of functional safety experts, and every now and then we get compared with other third-party assessors. And I always like to point out that we may not be the largest company, but we have the most functional safety people working for an assessment agency. So we're definitely the largest assessment agency when it comes to functional safety. Our product offering, we have consulting services for process safety. Think of the IEC 61511 world, the end user world, as well as for control system security along the lines of the ISA S99 standard. We do product certification for IEC 61508, as well as the ISA Secure scheme. And then we have a variety of training offerings in process safety, control system security, alarm rationalization that are either done online, offline, off-site, or on-site. Engineering tools, our main product is the Excellencia software, which contains a lot of functionality for example, process hazard analysis using the HAZOP methodology, alarm rationalization using a SIL selection, layer protection analysis, safety requirement specification, and so on. We also have some products that are more focused on manufacturers, for example, the safety case, and a software criticality assessment tool. And then we have our SILSTAT tool, which again is end user focused. A lot of reference material, a lot of books, databases that we have, and we do professional or personnel certification, or at least the Exeter certification portion oversees the certification of the people. The CVSE governance board handles the exams and the registration for the CVSD and CVSP programs. When it comes to the engineering tools, and we're going to be focusing obviously today on the field failure data collection methods, but when it comes to the engineering tools in the end user world, there's an alarm management tool, SIL Alarm. We have our PHAX software for process hazard analysis, SIL selection, safety requirement specification, SIL verification, and proof test specification, and all these tasks, all the tasks that this portion of the software focuses on are in the analysis and realization phases of the life cycle. And then we have our SILSTAT software, which is our data collection software, which focuses on the operational phase of the life cycle. SILSTAT, in a little bit more detail, the objective is to record field failures and store those in a database that we can use to further evaluate our original assumptions. So when we do the analysis work, when we do the realization work, we assume certain probabilities of failures, we assume certain demand rates, and the objective of the SILSTAT software is to record those events and then allow us to compare our actual performance with our assumed performance. As the SILSTAT software is developed by Exida, by the same development team as the Excellencia software, it shouldn't be a surprise that there's a lot of interaction between the two softwares, and any configuration that you've set up with the Excellencia software can be transferred to the SILSTAT tool. So you basically have a planned hierarchy, units, addresses of different devices in that plant automatically transferred into the SILSTAT software, and basically with a couple of clicks, probably 4 or so, you have a majority of your SILSTAT program configured. The objective is is that you are using this as an event recording, which is available as a recorder, which you would put on a laptop or a Windows supporting tablet. And there's a Windows desktop or a workstation piece to the software as well, where you can actually administer and configure your setup. There's a built-in failure taxonomy structure, and there's a lot of pick list selections that make it very trivial and easy to select items, to classify items. And all this data that you collect is used by Exida in its predictive analytics, and we'll talk about that in a little bit as well. And all the reporting that we create out of the SILSTAT software and the way that we handle the data in the SILSTAT software is compatible with the American Institute of Chemical Engineers Center for Chemical Process Safety, Process Equipment Reliability Data Initiative, or in short, the AICHE CCPS PERD initiative. There's a lot of reference material available on the market, and the majority of that reference material has been authored or co-authored by Exida people. And nowadays, we publish our own books. We are a publisher. We are able to provide ISBN numbers and things like that. In the past, some of our books were published through ISA. But as I said, most of our newer books are all published directly by Exida. For example, the Practical SIL Target Selection book was published by Exida directly. All right, so when we talk about field failure data collection, why do we want to collect field failure data? Or maybe a little bit more extensive, why do we want to record anything that's happening in real life with our safety instrumented systems? Well, in short, one could argue, well, we have to. The standard requires that we periodically compare actual performance with assumed performance. Now, at the same time, the standard doesn't really provide a frequency at which we need to do that. But if we take it a little bit closer home and see why would we want to record this event information. Well, we want to see if there's any compatibility issues with the application and the instrumentation that we've selected. If there are compatibility issues, that could be an indication of, well, there could be higher failure rates. We could have more problems with our system than we originally anticipated. Also, when we talk about the concept of prior use, which we may want to apply to a certain selection of equipment or justification of failure rates of that equipment in our particular application, then we need to have a good basis for that data collection. So we may want to look at prior use selection. The data that we analyze are process-specific, plant-specific data is stuff that we want to be able to use in a layer of protection analysis or in our probability of failure calculations. We may have average industry failure rate data that may be adequate. At the same time, it may be a little bit conservative, and we may be able to justify longer proof test intervals or fewer levels of redundancy and achieve the same level of safety integrity. So that's another reason why we may want to look at that data. Any improvements for maintenance could be flagged as a result of your data collection, and all this in the end should lead to higher process uptime. And of course, safety doesn't really pay the bills, it's an insurance, but in the end, what we want to achieve is high process uptime in a safe manner. So we want to record failure event data, and we want to record process event data. So some of our customers, they're doing a pretty decent job in collecting data, but in a majority of cases, that's when we talk to, let's say, headquarters. If you look at a main facility of one of our chemical company customers, they'll be doing an excellent evaluation of products, but it's only really for that one main headquarter location because there's enough people to support it. And in satellite plants, there may not be enough staff, or there may simply not be enough time, or there may not be an adequate procedure, or we simply may not know how to collect data. So, I visited a refinery a couple of years ago, and they had an excellent database of evaluated process relief valves. And the reason they had that, it was a requirement by ASME that every 3 years the relief valves were pop tested. So they were tested and everything was recorded. But when it came to the equipment on our safety instrument function, there was virtually no record, no electronic record at all. All the design information was on a probably 2 feet high stack of paper somewhere in a corner office. So no procedures in place, and then people just didn't really know what to collect. And we have some examples coming up as to what people were collecting and when, and how it could lead to optimistic conclusions. So why do we want to have a process and field failure event data collection process? Well, the initiative, or the incentive, is to save money. In the forms of having more process uptime. If you match your design to the risk, if you make sure that the equipment that you're selecting is suitable for your application, you have fewer problems with it, fewer maintenance costs, and so on. So the collection of real life data can help you identify potential issues in your plant. The functional safety life cycle, the functional safety standards, IEC 61508, IEC 61511, have two fundamental concepts. They have a safety life cycle approach, a detailed engineering process, and the probabilistic performance based on system design. So we're dealing with a rigorous development process. One could argue with the objective to eliminate systematic issues, typically software problems, and on the other hand, we are allowed to come up with solutions that match our risk, and we come up with these solutions based on probabilistic calculations, failure rates, and demand rates, for example. So those are focusing more on the random characteristics of our problems. When we look at the safety life cycle, a series of steps to be taken during the analysis, design, and operation of a safety instrument and function, with the objective to reduce design mistakes, increase safety, and in the end, optimize cost. You could say, well, I can skip the analysis phase completely by simply saying that I'm going to implement SIL3 safety functions. I'm not going to do any SIL selection. I'm not going to do any layer of protection analysis. I'm just going to say everything should be SIL3. Now, SIL3 is the highest SIL level in 61511, and you could argue that that's probably a reasonable approach, but at the same time, we probably all know that a SIL3 safety function is a whole lot more expensive than a SIL1 safety function. So the standard allows us, by following this rigorous process, to design our risk reduction optimally at an optimized cost. So if we look at the analysis phase in a little bit more detail, we're trying to answer the question, how much safety do I need? And when we are trying to answer that question, we have several pieces of data that we're looking for. We look for process data or demand data or past history when we're identifying potential hazards. We need to know demand rates and things like that. When we do our likelihood analysis, we need to know how often things fail. We need to know failure frequencies. And when we do our consequence analysis, we need to know, again, how is our process set up, and that's where, what are the impacts of certain events, and that's, again, where the process data comes into play. So there's a lot of input here for different data sources when we are trying to answer this question, how much safety do I need? When we go to the realization phase, all right, we're trying to answer that question, how much safety does my design have? So I came up with a conceptual design, I came up with a safety function that is protecting against a certain hazard, and when I determine how much safety I have, one of the inputs is failure rate data. Failure rate data for equipment that I selected as part of my safety instrument of function. And there are also maybe technology-related aspects when it comes to failure rate data, switches versus transmitters, for example. So again, it's an input source for failure rate data. Now, when we get to the operational phase, obviously I have a question, and that is, how will I keep it safe? And we can talk about performing proof tests, performing required maintenance activities, things like that. But one of the things that we should realize, when we are looking at the operational phase, that's an area where we will actually be able to obtain failure data. And when we are doing our maintenance, when we are doing our proof testing, and we detect that something is failing, we can record that failure, and we can determine what failure rates are applicable for a specific piece of equipment. So this is an area where we would actually obtain failure information. So again, back to that field failure data collection. One of the things that we need to ask ourselves is, what kind of systems exist, and what kind of system should we have? So what did we come up with in our design, and what do we really have in our installed field? So as part of our assessment work over the last decade or so, we've been able to evaluate a lot of field failure data from both manufacturers and end users. And the quality of that information is not always the same, but it's a lot of information that we've been able to review in detail and look at how systems behave when they're in the field. And over that decade, we've been able to collect over 100 billion unit operating hours. That's a lot of hours of operating experience for different pieces of field failure equipment. And all that information was based on many systems, many different applications, and we learned a lot. And I say we learn a lot, but also the manufacturers learn a lot as to how their systems are being used in the field. So a couple of examples. We have an extensive set of test results from a test shop indicate that a manufacturer had an exceptionally low failure rate. Well, that's great news. You have average industry information, average environmental exposures will suggest a predicted failure rate. And if the actual failure rate is a whole lot less than that predicted failure rate, that's obviously good news. However, when we visited the test shop and had them look at, or had them demonstrate how they came up with, or how they evaluated the field failures, we noticed something. And the key thing that we noticed was that before they really started the testing of each unit, they cleaned it. And the cleaning, meant in some cases disassembly and replacement of seals and O-rings. If those are areas where failures occur, then yeah, I can see by replacing those before you start testing that you end up with a whole lot lower failure rate than originally expected. So take it the other way, take the opposite approach. If you clean it up, if you fix the unit before you start testing, it's really surprising that any units failed after all this refurbishment activity. So in this case, the exceptionally low failure rate wasn't a real field failure rate. It was a failure rate after the refurbishment. And arguably this would support the claim that a maintenance capability, or taking into consideration the performance of your maintenance crew, is something that we should take into consideration, because apparently in this case not all failures were fixed with this cleaning up activity. So lessons learned: the test, repair, and data collection process must be understood to correctly analyze field failure data. If we don't understand how that testing, repair process goes while we are evaluating the data, then we may come to the wrong conclusions. And in this case, as found conditions were not recorded. So key problems were potentially already removed before the unit was tested. Another example, data from an on-site repair shop is entered into a maintenance management system where equipment failure rates are automatically analyzed. And that maintenance management system reports showed that the failure rates were much lower than those provided by the SIL verification tool, in this case Excellence, or to be a little bit more precise, the Safety Equipment Reliability Handbook used failure rates, as a collection of failure rates, and those are used in the Excellence software. And those failure rates in the Safety Equipment Reliability Handbook were a lot higher than the MMS report suggested. So a conclusion was, hey, we can extend our proof test intervals, and that would not impact safety. So failure rates are lower, and in your simplified equation, the probability of failure on demand is the failure rate times the test interval divided by 2, the average probability of failure on demand. If your failure rate goes down, your test interval can go up, and your probability of failure remains the same. So that conclusion may be correct. However, before they actually went in and said, you know what, we can extend these proof test intervals, we had an instrument engineer visit the test shop. And what did we discover? Failure reports were entered into the system only when the device was sent out for repair. So only when a work order was needed, or basically a purchase order is maybe the better term here, only when a purchase order was needed, when one had to spend money to fix something, was it recorded in the system. If the unit was repairable in the shop, then they just simply did it and did not record it. Compared it to transmitter, transmitter sometimes you may have an issue in the transmitter if you just power it down, power it up, and it works again. In that case, it was not recorded. But if powering down, powering up, and the issue remained, then it was recorded. Well, the powering down and powering up and it works again, that is, of course, a failure of the transmitter that should have been recorded. That is an issue that we should document and take into consideration. Maybe an indication of a systematic issue with that transmitter. So, as a result, the data in this maintenance management system was very optimistic. The proof test interval was not extended as a result, because we realized that this data was not complete. So again, we need to understand how the data is collected when we analyze the data. And we also need to understand the as found conditions for all failures, and the test must be recorded. So again, lessons learned. Another example, and I think this is our last example here. A field failure study of a valve showed a low failure rate when compared to the Exeter predictive and analytics benchmark. Or that's when we evaluate a product as part of our 61508 certification work, we end up with we predict a failure rate based on the design of the product. And in this case, the field failure study showed an exceptionally low failure rate, and one would say, hey, this device is behaving a whole lot better than predicted. However, again, looking at where did the data come from, how was the data collected? Data was the valve was originally designed for control applications. And even though the analysis report did not really state it, it was expected that the data that was gathered was all based on dynamic operating conditions of a control valve. The valve is continuously moving. Whereas in safety, our main issue is the static application. That valve is sitting there open and it's not moving at all. Only when there's a demand from the process will we ask that valve to move. So stiction problems, we're not looking at. Your typical stuck stem, those things, those failures will not be detected or will not be recorded in a dynamic operation application. So in this case, failure rates that were recorded will simply not be applicable to static applications. So we need to look at where's the data coming from. Now, if you use a transmitter for control applications and a transmitter for safety applications, you could probably argue that the control experience is the same type of experience as you have from your safety application, because they're both measuring a process value and sending you 4 to 20 milliamp signal. But clearly, in the final control element, where a valve is continuously moving versus a valve being static, that is not the same application. So in this case, what we learned, you need to document your application conditions and make sure that you know what the data, what your conclusions are based on. So when we look at some of the existing field data collection systems, one of the disadvantages or negatives that we see is the variety of the amount of data that's being collected. In some cases, it's only collected when there's a purchase order associated with it, or in some cases, data is only collected if there's a work order associated with it. If I can use a hammer to bang on a valve and the valve is fixed, quote unquote fixed, then that may not necessarily be recorded. Different definitions of a failure. So for control applications versus safety applications, that may be an issue. The categorization of different technologies. I may have a temperature measurement in a transmitter. That's not going to behave the same as the temperature measurement in a switch. And also an issue that we saw is the lack of fault isolation. So identifying where the real problem is. What the real causes of the problem. So after we looked at dozens and dozens of field failure studies, we recognize a lot of problems with data collection, and the results, when your expected failure rates or expected demand rates could be orders of magnitude different. And if you use that information, you could end up with an under-designed system. So what we need to know is, when is a failure report written? What is the definition of a failure? Do we record the as-found conditions? And what were the operating conditions? So in some cases, when we talk about pressure relief valves, the pressure relief valves are disconnected from the process. They're disassembled, moved to a test shop. We need to, we may do an immediate pop test, but one of the things we need to evaluate is, do we really have the as-found condition when we disconnect that pressure relief device from the process? So those are things that we need to look at, and obviously operating conditions need to be recorded as well. IEC 61508, Part 2 of the 2010 version of the standard, in Clause 74433, lists a variety of field data collection standards. And there's an ISO standard, there's an IEC standard, there's the German NAMUR, NE93, the Nachweis der sicherheitstechnischen Zuverlässigkeit von PLC Schutzeinrichtungen. standard, and then we have the PERT initiative from the ASCHE. So there's some different field data collection standards that are published. If we look at the ISO 14224 and the IC 60300 standards, then they have requirements, basic requirements for collection of data, but it's not enough for functional safety. It's not enough for your safety instrumented systems. It doesn't go into the level of detail that we would like to see, so that we can eventually justify economic optimization of your applications. Another as part of this clause 74433 and 61508 is the concept of root 2H, and 2H is a alternate method to your minimum hardware fault tolerance determination instead of, say, failure fractions and equipment type A and B. And it talks about the confidence that you have on a piece of failure rate, and it identifies that we need to look at field feedback for equipment in use in a similar application environment. So we need to make sure that when we are using data from field experience, that it really applies to our specific application. And it also talks about that there may be needs for some expert judgment. So we may not necessarily be able to automate all of these data evaluations. And one of the things that we went through a pressure relief valve assessment at a site here in the U.S. And we came to the conclusion that we could have concluded an average probability of failure for a relief valve, but in reality there was a strong indication that the specific location in the plant was a contributor to the probability of failure of that relief valve. So some locations were really awkward. It was difficult to mount the relief valve on the process, and there was actually higher failure rates for that particular location versus other locations in the field. So some of the data we simply need expert judgment to come up with adequate conclusions. So when we are talking about a field data collection system, we need to realize that we need to identify the components, adequately identify the components, different types of technologies. We need to know what are transmitters, what are switches. We need to record the operating profiles and physical environment so that we can see if data collected in one application is the same or is applicable to another application, maybe in a different location, geographical location. We need to record the volume of the operating experience. We need to know how much experience we have with a particular piece of equipment, because when we look at confidence intervals, the larger the number of samples, or the larger the operating experience, the narrower the confidence limits will be. In other words, if you have very few information or very few data samples, your confidence limits will be very wide, and data may not be that useful. You need to know proof test methodology. You need to know proof test coverage. You need to know bypassing time. When you talk about proof tests recording, you need to know what was assumed in the calculation and what's the actual time. And in the end, we want this whole process to take less man hours than current methods. And so we need to optimize a field data collection system so that we have the information that we need, but at the same time that it doesn't take as much time as we typically see. So when we talk about identifying a component, we need to know the manufacturer, the model number, the serial number, and we want to be able to follow that component throughout the life of the plant. So for example, if I have a transmitter that failed after a certain period of time, and I send it out to the repair shop and it gets fixed and it goes back into the stock room and it eventually goes back into the process, I want to be able to follow that that particular device and see if that particular device maybe in the end had a manufacturing issue that caused it to fail, or maybe it is a random failure that was the original problem. I want to record operating profiles and physical environments. Where's the component installed? Where's the actual physical location in my site? And that goes down all the way to the tag number. So I need to have an overview of plant addresses, plant tags, and devices, and I need to know which device is linked to what particular address. And I know you can have different levels of collections, like units and plans and sites, etc. But in the end, it comes down to that unique address, that unique tag number in a location that defines its physical environment. Now, we need to know for that particular device, when was it commissioned? When was it decommissioned? What was its operating duty? Was it running continuously, or was it running intermittently, or type batch type process or a continuous process? Based on that, we can determine what the operating experience is, or the hours of operation experience that are applicable to a particular device. So there's the physical address, there's device-specific information, and then there's the device use information that I all need to gather as part of my field failure data collection system. And then there's a bunch of different events that we can see. Obviously, the majority of events that we'll see are probably proof tests. Now, when you do your SIL verification, you come to the conclusion that once a year you need to do a proof test. That's the event that will take once a year. You don't expect a failure every year, but obviously a failure could happen. But you want to record each and every one of these proof tests. And when we started to work on our SIL-Stat software, the main objective was to be able to collect field failure experience, live events. How often does a unit fail or a piece of equipment fail? How often is there a demand from the process, so that we can compare this to our actual or to our assumed performance. But at the same time, we started to realize that one of the things that we as an end user need to do, we need to record and document that we've executed proof tests, that we've executed mandatory maintenance activities, and as part of your event recording in our SIL-Stat software, for example, you can record that the fact that you've done these proof tests and that they passed, and at what date you did it, and who did it, etc., etc. So, what are the types of events? Typically, your proof tests. Those are the main ones. But there may be specific maintenance activities. If you have an issue with plugged impulse lines, you may want to schedule a maintenance activity to periodically clean out those impulse lines. Or if you look at specific gas sensors, the actual gas sensing element may need to be replaced once every 3 months. That's a maintenance activity, and you want to keep track that you've done that. So that if there's a failure, you can at least rule out the fact that, hey, the sensing element was indeed replaced in time. It's not a wear-out issue. Any diagnostic events, any indication from a piece of equipment that something is wrong, you want to record that. Then process demands, actual trips, something is going wrong in the process, and you want the safety function to go to the safe state. That's something that you want to record. But you also want to record that basically from the beginning. So if the original hazard is identified by, let's say, high pressure, and you have a control function that reacts to that high pressure as an interlock, you want to record that. You want to record that your layer of protection was successful. Or if that layer of protection failed and there's an operator that is supposed to take action, you want to record that that operator was successful or failed. And if that operator failed, that your safety instrument function was successful or not. And if that safety instrument function failed, that your pressure relief valve was successful. So, we sometimes tend to focus a little bit too much on the safety instrument function itself, but when you extend that and look at the hazard scenario, there are many layers of protection that will protect against a specific hazard scenario, and you want to record which layer was successful. And in the end, that information as to the success rate of your different layers of protection is used in your layer of protection analysis. Any process offsets or false strips, you want to record those as well. Now, if a unit causes, or if a specific piece of equipment causes a lot of false strips, maybe something wrong with that unit. All right, it's not dangerous, but at the same time, there goes your uptime. So we need to record the event types. We need to determine and record who worked on it, when was it removed from service, when was it restored to service. This, when you remove a device from service, that goes against its operating hours. You want to keep track of that, and any other data that is really event-specific information. So, for example, we could talk about error codes for transmitters. When we talk about a proof test, obviously, if a proof test is successful, meaning everything passed, then you want to record that you've executed the proof test and that at the date that you executed and that all steps of that proof test passed. If there's a failure during the proof test, then you want to document the as-found conditions. Why did something fail? So you can answer that question. Any possible causes? What was the time of failure? Who worked on it? Is there any work order associated to this to fix it? And when was the unit put back in service? Is the unit replaced? Is it fixed in the field, and so on? So those are the type of information that you want to record there. So one of the ways to reduce a lot of the work associated with the maintenance events is basically to create a tag or address database, an indication as to what your plan layout is and what the different pieces of equipment are that are in your plan. And a lot of this information, and you see an example here on the right-hand side, a lot of this information you kind of know from your SIL verification. You may know calibration ranges, you may know a particular model number that in this case we talk about a temperature transmitter, you may know a specific tag and so on. So a lot of this information is already known when you come up with your conceptual design. And then again, when Excellencia and SILSTAT work together as a seamless export of that information, your plant hierarchy is automatically populated. So a lot of this information is available early on. Now, when you do your commissioning, then you will know the actual serial number, then you will know your commissioning date, then you know the environment where you may have a set of 4 potential environmental profiles that you can pull from, an operational percentage, 100% continuous operational batch process, and so on. So a lot of that information may already be known during the conceptual design phases of your safety life cycle. When it comes to the event data collection, now what type of event is taking place? Is it a proof test? Is it a maintenance activity? And the activity could be something similar as a proof test with multiple steps. It could also be a simple, hey, I'm removing this device from service and I'm replacing it because there's the end of useful life is reached, or there may be a process demand that I that I need to record. So a lot of this stuff can be automated, and your tests can be recorded in a proof test. Your maintenance activities steps can be recorded in a maintenance activity, and so on. And it's very straightforward to record these in a system. So you combine your address or tag database with the actual event data. So in the address, you have the physical location. You have devices that are assigned to that physical location and are potentially removed from that physical location. The physical location is pretty static, of course. The device may be coming in and out. And on the other end, here on the right-hand side, you have your event data record where you may have a proof test that was performed. You may have a failure that was identified with a potential cause, and you record the failure date and things like that. The data eventually is going to be stored in a database, and of course, this is an example of an early draft of our SILSTAT software where we're looking at a replace activity as a maintenance activity where a particular device was replaced from service, was removed from service, and a new device was put in, and that type of information is available in a database, or should be available in your database. When it comes to the evaluation of the data that you've recorded, we need to realize that expert knowledge is going to be needed. Reliability engineers can typically recognize quality data, and they will be able to evaluate the actual results as recorded in a very thorough method to make sure that your conclusions are adequate. That if you conclude that you have a low failure rate, lower than average industry, that is based on a solid background and not because you didn't record all the information. We use a set of techniques that we've all combined into a method that we've named predictive analytics. So all our failure rate estimates are based on this predictive analytics concept. And we use detailed models of each device type, ranging from transmitters to valves, and we compare field failure data for a particular product with what we would expect that product to yield as a result of our failure mode effect and diagnostic analysis. So we have an estimated failure rate, we have an actual failure rate, and we compare the two. If there is a significant difference, then we want to understand why. So we dive into more detail in that field failure information. Now, we've given a couple examples where the field failure information suggested a lower failure rate than the actual predicted failure rate, and we found some issues with the collection data. We've also seen the opposite, where the FMEDA predicted failure rate was lower than the actual experienced failure rate. So the field failure rate suggested that the failure rate should be higher than what we predicted. And then when we looked into those cases, what we typically found were systematic issues. And in one case, we were talking about I think it was a fire detector, and they had a lot of issues with water ingress. So a lot of the units failed because of short circuits due to water in the units. The problem, of course, here is the design issue that water can get into the units. And in that particular case, now a solution was found where the unit was better sealed and water couldn't be sucked into the unit anymore. And as a result, those groups of failures basically no longer occurred. That's an indication of a systematic issue. So your field failure data could show a significant difference to your predicted failure both ways. It could be due to poor collection or not an adequate collection method. It could also be because there are systematic issues. And then, of course, if there are systematic issues, you want to address those and fix them. And as the property of a systematic issue, once you've addressed it, that problem goes away. So that's an indication, hey, systematic issue's been solved. That should immediately lead to better uptime, process uptime for your unit. So when we talk about failure data collection, a good data collection system can be implemented without major expense. And I've seen some systems being implemented where once the system is installed, there's months and months of effort needed to basically configure the systems to allow that system to be used in the actual site. What we've done with Excellencia and Silstat, you can simply export your Excellencia information into the Silstat software, and you're basically ready to go from day one. There's very little setup required to record your safety instrumented system information, hazard scenarios, laser protection, your actual safety instrumented function and its proof test. All that information can be transferred from Excellencia into Silstat. A good data collection system with predictive analytics can provide consistent results across many sites and applications, and that's key. If you make sure that your collection systems are adequate, then your conclusions from site 1 may be applicable to site number 2, and your performance basis has a real planned set of information that it can be used. I have a question that's coming up. Is it possible to transfer device data from an asset management system, the safety instrument system, or another software such as, and I won't use any specific manufacturer suggestions here. There are importing capabilities into our SalesTech software. Yes, absolutely. It's optimized obviously for Excellencia, but yeah, general import is definitely available. There are some import schemes that some need to be defined a little bit better at this point, but there are some importing schemes that they can use from basically Excel spreadsheet or CSV files directly. So yeah, that is available. So again, when we look at our field failure data collection, there is a clear incentive to save money, identify systematic issues, and also record the fact that you're compliant with your conceptual designs, that you've done your proof tests. The key, of course, is to the success of your data collection is to reduce the cost of data collection and achieve high quality results. Make sure that everything is recorded. Make sure that that anything that any data conclusion, any resulting report is complete, and that you have adequate conclusions. So that wraps up our data collection webinar for this morning. Rerun this afternoon. If you have any questions regarding data collection and analysis, or if you have any questions regarding Excellencia, feel free to ask them right now, or Excellencia or SalesTech, I should say. For our software tools, we have a support website at support.exada.com where you can raise a ticket, a support ticket, and we can address that. If there are any questions related, in general to data collection, feel free to ask them now through our Q&A, or later. We're happy to address any questions. Probably easiest way is to send them to us in email at info@exada.com. So info@exada.com, and we're happy to address those questions as well. Well, thank you for attending the webinar. If there are any other questions, feel free to ask. I'll be hanging around for just a little bit more. If not, thank you for attending, and hope to have you listen to one of our future webinars again. Take care.